Thank you for the kind introduction. I'm really honored to be here today in this, to present my work in this prestigious conference. And in a while we will have also the slide. We should finish about at 7:30. Don't worry, we are just losing the appetizers, probably. Thank you. I've been asked to speak about in silico mitral valve repair. This is actually what I'm doing since 1996, and I'm still going on. So I think that I'm quite ready for this speech. I was, at that time, I was a young postdoc, and Professor Alfieri from San Raffaele Hospital asked me to simulate the behavior of the mitral valve that had been treated with edge-to-edge, with the edge-to-edge technique. And well, that was the start of the adventure, and I was really fascinated by the world of valve repair. That was something new for me. I was an engineer. I'm currently still an engineer. And well, this experience switched me from the objective of creating new devices and prostheses to the objective of creating new tools for clinical decision making. Since what I realized is that actually engineering tools can be really useful to provide quantitative data, and this has been discussed widely this morning in this concession, and also to investigate possible outcome of a specific procedure. So, in perspective, to choose, to be able to choose the patient-specific optimal solution. Indeed, let's say patient-specific modeling is the holy grail of this decade. We started in the, let's say, modeling started in the early 90s, working on simplified models. But simplified is not so cool. Then we moved to paradigmatic models. Then in the 2000, we arrived to define what real models based on average data. And now there is a strong push towards patient-specific modeling. By the way, in the 2017 program of Horizon 2020, there are several calls dealing exactly on patient-specific modeling as clinical tools for surgical decision-making. And, well, patient-specific is for any kind of surgery, but it's particularly appealing, at least for me, concerning valves, cardiac valves. That is because despite their structure is very complex, it has been described in a very detailed and fascinating way by Pedro Del Nido this morning. The way it functions is strictly related mainly to its geometry and to the way the different components coordinate each other. And also surgery is mainly related to geometrical factors. We find the objective of the surgeon is to find that geometry that can restore the function of the valve. That is not necessarily the original one, but it must go in that direction. And in the majority of the cases concerning modeling, the geometrical factors are much more important than other factors like the tissue behavior or the blood constitutive behavior. So we need good imaging, and we can create reliable models. That is the principle, but the first take-home message is don't trust critically numerical modeling, since these are empirical models that are based, whose reliability is based on the hypothesis that we do to build this model. So if we have good data, input data, we will have reliable results. But this is not always the case. So Now we can move to the roadmap that brings an engineer together with a surgeon from the imaging acquisition to have a good model for replicating a surgical procedure. We need repeatable criteria to acquire mitral valve anatomy. This is not trivial at all. It has been discussed again this morning. Different radiologists can obtain, or cardiologists can obtain very different measurement from the same data source. So we need a robust, possibly automated method to extract information from imaging. Second, we need the mathematics. This is up to the engineers and to mathematicians, but we have now very reliable models that just need to be fed correctly. And at the end, what we can do is to extract those data that can be useful for the surgeon, that are typically coaptation area, coaptation length, cord tension, leaflet tension, and so on, and of course also the dynamic of the valve. So let's start briefly from the first step, the imaging. Really, in this field, we started with 3D echography, but the world was not mature for that. It was really a mess to obtain the raw data. So we moved to MRI. MRI is considered the gold standard. Unfortunately, is not the standard of in many clinics, but it's the gold standard since we have a high spatial and temporal resolution image. We can capture all the detail together. We can have information about the gadolinium uptake, so about the necrosis, and also we can have through the 4D flow sequence information about the flow rate and the velocities. On the other side, as I said, unfortunately, we often don't have the follow-up, the MR follow-up of the patients that we study, because the patient don't tolerate very much this procedure, since very often we have a pacemaker implanted in the meanwhile, so they are no longer eligible for this kind of imaging. And so let's say we waste half of our patients at least. The alternative is Eco3D. Eco3D is now almost the standard in clinics. It has some drawbacks. Well, concerning temporal resolution is quite close to MR imaging. Concerning spatial resolution could be even better, but the signal to the noise to signal ratio is still high. Sometimes we can't get the whole ventricle, so we miss, for instance, the papillary muscles if we want to look at the valve. But it has also some fantastic features like this. We can really get the geometry of the geometry of the leaflets. Not only the geometry in detail and through the cardiac cycle, but we can also get information about the thickness that can be really relevant concerning some kind of pathologies. So at the end, we can obtain map through time, through times of the thickness of the valve, for instance, for a Barlow disease. These information are extracted through specific tool that we develop to automate as much as possible the geometry acquisition. This is an example of a tool that we have developed in a European project 3 years ago. We can get with this tool the annulus dimension, the leaflet profile, the papillary muscle position. If we want, we can also track the entire ventricle. And by using a specific sequence that is a rotational sequence that rotate through which we obtain the plane by rotating them along the ventricular axis, what we obtain at the end is an information about the annulus shape and about the papillary tip location. And if we integrate it through times, what we obtain is the motion of the annulus and of the papillary tip during the cardiac cycle. So at this point, this can be done with the MRI, can be done also with echo now. At this point, when we have the acquisition, we have the segmentation, what we need is the model. And the model is obtained by collecting the information about the leaflet length in one time frame and by creating a surface that mimic that lie on the profile that we have collected through segmentation. And at the end, we add the chordae tendineae. With these models, now we can just apply the pressure and simulate what is going on. And I will provide now two examples. One is about annuloplasty. What you see in the next slide is an ischemic mitral valve with a regurgitant area, lateral regurgitant area. This is a functional mitral regurgitation. And well, on this valve, we can apply, for instance, two different strategies of correction by using, for instance, two rings that mimic the behavior of currently available rings on the market. Here is the simulation. We simulate the sewing of the leaflet on the annulus in both cases, and then we apply the pressure and we observe the behavior of the two valves. And in this slide, I show you the case of three patients, again, ischemic mitral regurgitation. Patient 1 is the one that we have just seen. And all three have a lateral mitral regurgitation. And as you see, both the rigid and flexible rings apparently are able to correct perfectly the regurgitation. But indeed, if you go into the detail, in this case we have just cut the leaflet in order to see the profile in the mid-valve. What we see is that the choice of the ring is not neutral, and depending on the patient, one solution can provide a higher coaptation length than the other. The second example is MitraClip. We have talked about MitraClip in the last 3 talks. So let me start with, not with a simulation, but with a 3D echo. This 3D echo is, let's say, good quality, but there are some emboli, apparently. These are actually air bubbles, since this is not a real life or patient heart. It's porcine heart taken from slaughterhouse, and that is one of our mock loop that is present. Okay, it's shy. That is present in our labs. This is an engineer. This is a surgeon, and what we do with this mock loop is to perform standard clinical imaging like fluoroscopy or 3D echo, but also insert fibroscopes and look at what is going on in the ventricle during the surgical procedure from the atrium and from the ventricle. In this way, we give the opportunity to see what is going on, what the surgical action is translated into the heart, and to compare what is the echo imaging with, and also the fluoroscopic imaging with what is actually happening inside. This kind of imaging is useful and ophthalmoscopy is useful for training, of course, and is also useful for checking new technologies and new ideas. For instance, I think it could be a good system to check the application of the melody in the mitral position, just using small hearts. But unfortunately, it is not able to give us information apart those about fluid dynamics. For instance, we can calculate the coaptation area, the coaptation length, the strength, the tension on the chordae, or the stresses on the leaflets. For that, we need computational modeling. And this is an example of a leaflet that is being in which we have simulated the mitral clip up position and where we are calculating the stresses. What's the use for? Well, for instance, we can try to answer to a question that has been raised several times concerning mitral clip. What if the grasping is not perfect? So we could simulate different grasping procedures, different grasping levels. 100% is the optimum surgery, 25% is the worst, and some average. And what we can calculate is how this is detrimental concerning, for instance, the coaptation area. And we see that only in the third case we have a strongly reduced coaptation length on the anterior, posterior, on the anterior part. And we can calculate the stresses, of course, during the diastolic flow peak, again, and compare it with dangerous level of stresses. And what we can do also is to simulate different level of lateral mispositioning of the mitral clip and see again what is the regurgitant area, if any, what is the coaptation length, and what are the stresses. And of course we can, and this is the beginning of the story, 1996, but it's still valid now for the mitral clip, we can, of course, also evaluate the fluid dynamic, the degree of stenosis for that patient, and so on. So let's go back at the end of my talk on the main question, are these methods reliable? The validation is really very hard. I would say that it will be just the completion of a large database. We saw today a database of thousands of cases about ventricle. It was an amazing work that was shown today. Here I will show just three patients. These are there is something. Okay, these are the profile of the anterior and posterior leaflet taken from segmentation. And here we have the anterior and posterior leaflet profile obtained with simulation. Consider that in simulation we always start from the open valve and then we simulate its pressurization. And well, I would say that the results are at least encouraging. So I would like to thank all the people of my group that partly collaborate on this project or on similar ones. I would like to thank the European Union supporting this study, and of course I would like to thank you for the attention.